Welcome to AXOR Galactic Observatory, where Artemis II may have witnessed 6 impossible lunar impacts. Before any flash, the real question is whether near-Earth debris is quietly thickening over all. Scientists first study the sporadic debris background, because ordinary flux shifts matter more than spectacle. On Earth, fireball records reveal patterns, but only caution can turn counts into evidence carefully. Atmosphere, daylight oceans and uneven witnesses filter fireballs hiding much of the true influx above. The Moon offers a cleaner detector because impacts reach its surface without air weather or noise. During eclipse darkness, Artemis II could see much more of the lunar night side at once. Those reported flashes are striking, yet brightness alone cannot settle their energy or meaning today. So the mystery deepens between observation and conclusion, where better visibility still hides certainty easily. Greater lunar coverage helps, but human vision stays limited, leaving baselines suggestive rather than decisive. Around the mission, active solar conditions raised radiation context and operational concern beyond the Moon. Beyond low orbit, Earth magnetic shielding weakens, exposing cislunar travel to harsher particle conditions there. A nearby asteroid flyby adds drama, but coincidence alone does not prove physical connection here. Then the story turns homeward, where lunar distance makes every return faster, hotter, less forgiving. Returning from the Moon demands higher entry energy, stronger heating, and tighter trajectories than orbit. After Artemis I, unexpected char loss and gas escape limits forced serious heat shield reassessment. NASA revised Artemis II re-entry using trajectory changes to reduce risk and better protect crew. Now 2 readings emerge, and both survive because the evidence remains incomplete but meaningful today. One reading stays cautious, another sees a changed environment hiding behind several aligned signals already. For now, Artemis II offers disciplined uncertainty, a rare human observation inside a larger puzzle. Like, subscribe, and thank you for listening. Now we open the wider debris field first. Far beyond the weather of Earth, and beyond the thin human sense of a calm night sky, the near-Earth environment remains full of motion. It is not empty space in any ordinary sense. It is a moving field of dust, grit pebbles, fractured stone, and occasional larger bodies, all following paths shaped by gravity-heat collisions and long spans of time. Some of this material comes from comets that shed dust as sunlight warms their surfaces. Some comes from asteroids that collide and leave behind trails of fragments that continue to circle the Sun. Some drifts inward over ages as sunlight exerts a small but persistent force on tiny grains, changing their orbits bit by bit until they cross the path of Earth. The result is a background environment that is never truly still. Planetary science describes this broad population with words such as meteoroid, interplanetary dust, and sporadic source. A meteoroid is a small natural object moving through space, usually smaller than an asteroid, and often much smaller than any object that would survive intact to a surface. Interplanetary dust is the finer part of the same general system grains, so small that they behave almost like a haze spread through the inner solar system. A sporadic source is a direction in the sky from which many meteors seem to arrive, not because they begin there, but because orbital geometry makes unrelated particles appear to stream from similar regions when Earth moves through them. This background matters because it represents the ordinary bombardment of the inner solar system. It is the constant low-level traffic of material through which Earth, the Moon, and every spacecraft must pass. In ordinary public attention, dramatic objects dominate the imagination. Yet those notable events are only the visible crests of a much larger and quieter system. Most of the material moving through near-Earth space belongs not to spectacular one-time visitors, but to persistent populations that remain in circulation year after year. They are the debris field left behind by the long history of solar system formation and the continuous grinding of small bodies ever since. Over long timescales, the environment renews itself and erodes itself at the same time. Larger fragments collide and become smaller ones. Smaller grains absorb light and slowly migrate. Some particles are swept outward, some fall inward, and some cross the routes followed by planets. Near Earth, this means that the space around the planet is neither dominated by random chaos nor governed by a single clean pattern. It is structured, but that structure is statistical rather than simple. Scientists can identify broad sources, recurring showers, seasonal variations, and typical ranges of speed, but any given hour still contains a wide range of possible arrivals. One particle may move at many kilometers per second relative to Earth, while another enters much faster, carrying far more energy simply because speed rises inside the kinetic equation so strongly. Even a small object can release striking energy if its velocity is high enough. This is one reason the background population deserves more attention than it usually receives. A change in that background would not mean the sudden arrival of a single menace with a neat name and a plotted close approach. It would mean that the baseline state of the environment itself has shifted. That kind of shift is scientifically more important because it affects not one isolated event, but the probabilities that govern many events. It would alter the expected rate at which small bodies encounter Earth, graze the atmosphere, strike the Moon, or pose a risk to hardware operating outside the deepest shelter of Earth's magnetic and atmospheric protection. It would also be harder to interpret in public because there would be no single culprit to point toward. The danger, if there is one, would lie not in a dramatic exception, but in a subtle increase of ordinary traffic. A single large object on a known path can be tracked, modeled, and discussed as an individual case. A denser background of smaller material becomes instead an environmental condition. It behaves more like weather than like a singular disaster. This is why scientists care about baselines. A baseline is the long-term average state against which a possible change can be measured. Without it, a surprising cluster of events remains only a cluster. With it, the same cluster may begin to look like evidence. Establishing such a baseline in near-Earth space is not easy. The debris field is uneven in size, orbit composition, and source. Observation methods also differ. Radar catches some particles. Optical surveys catch others. Atmospheres erase some evidence even as they create visible meteors from it. Airless surfaces preserve impacts in a more direct way, but only when they are observed under the right lighting conditions. Spacecraft encounter still smaller particles that may never be seen from a planet at all. Each method reveals one slice of the environment and leaves another in shadow. The broad picture emerges only when many slices are compared over time with patience and restraint. In that broader picture, the calm appearance of cislunar space becomes misleading. The region between Earth and Moon often looks visually serene, a place of black distance and silent light. Physically, it remains part of the same inner solar system traffic flow as every other orbit near the Sun. Dust crosses it. Small stones cross it. Fragments whose origins may lie in ancient collisions or distant comet passages continue to move through it, whether or not any observer is present to notice. The outer frame of this story, therefore, begins not with a single spacecraft or a single flash, but with an old and ongoing condition, a planet, its companion moon, and a corridor of space existing inside a persistent cloud of natural debris. Most of the time, that cloud expresses itself quietly. It leaves faint meteors, microscopic pitting, slow surface gardening on airless worlds, and occasional bright events that seem unusual, only because human eyes rarely witness the full pattern. The essential scientific task is to decide whether the pattern remains within its expected range, or whether the background itself is becoming more crowded, more energetic, or differently distributed than before. In a system built from countless small bodies moving on intersecting paths, that distinction carries the greatest weight. On Earth, the broad debris environment does not arrive as a direct count of objects moving through space. It arrives translated through atmosphere, light, geography, population, and attention. This is why long-running fireball records matter so much. They do not provide a perfect measurement of the incoming flux, but they offer one of the few continuous ways to watch for shifts, large enough to rise above the noise of ordinary variability. A fireball, in practical observational language, is an unusually bright meteor, bright enough to stand out strongly against the night sky, and sometimes bright enough to cast shadows, leave a persistent glowing trail, or produce sound after the light has faded. These are not the faint, brief traces that appear during an ordinary meteor shower to a watcher who happens to be looking upward at the right moment. Fireballs are the more energetic events, the larger or faster entrants whose passage through the atmosphere creates an effect visible over wide areas. Because of that visibility, they are more likely to generate multiple reports, camera recordings, and enough information to support later analysis. Over many years, those reports become a dataset. In North America, one of the most important collections of this kind is maintained by the American Meteor Society, which gathers public reports of fireballs and also draws on dedicated all-sky camera systems. The value of such a record lies not only in single spectacular events, but in continuity. A lone bright fireball proves very little about the underlying environment. A sustained pattern across months or years treated with statistical caution can suggest that something more structural may be happening. This is why databases matter in astronomy, even when they appear plain on the surface. They preserve repetition. They turn scattered moments of surprise into something that can be compared across time. Yet the usefulness of a long record depends on discipline. Raw totals are never enough by themselves. More people, more cameras, better phones, broader internet access, and faster reporting all increase the number of events that are noticed. A rising count can therefore reflect better observation rather than a physical change overhead. Any serious reading of the record must begin by separating the instrument from the sky. In this case, the instrument is not only hardware, it is also the human reporting network where people live when they are awake, whether clouds are present, and whether a bright event occurs over land rather than ocean. A fireball over a major city during clear darkness may produce a flood of observations. The same event over empty water may pass almost unrecorded. This does not make the record useless. It simply means the record must be interpreted as a filtered measure of reality rather than reality in a pure form. When scientists look for anomalies in such a record, they search not only for an increase in total reports, but for changes in the character of the events, and for signals that remain after known reporting biases are considered. A carefully treated anomaly therefore involves more than a larger number on a chart. It may include changes in witness counts, event brightness duration, acoustic conformation, geographic spread or directional clustering in the sky. Each of these properties carries different information. Brightness can hint at the energy released during entry, though the relation is not simple because angle, speed, fragmentation, and atmospheric behavior all matter. Duration can suggest how long an object survives while descending through the air. Widespread reports can indicate either high brightness or occurrence over populated regions, and sometimes both. Sound reports add another layer because a sonic boom implies a certain scale of atmospheric interaction and survival deep enough into denser air to generate a pressure wave that reaches listeners on the ground. In the first months of a year, if a record begins to show not just more fireballs, but more widely witnessed ones, more long-lasting ones, and more acoustically confirmed ones, attention naturally follows. Even then, the correct response is not immediate declaration, but careful testing. A trustworthy anomaly is one that survives attempts to explain it away through improvements in reporting infrastructure alone. This is what makes long-term observational institutions valuable. They provide both memory and method. Memory allows comparison with earlier seasons, earlier years, and earlier cycles of skywatching. Method allows the same record to be treated not as a collection of stories, but as a structured observational history. The resulting picture is still incomplete, but it becomes far more informative than any isolated event ever could. There is also a quieter value in this type of record. It preserves the intermediate scale of cosmic activity, the range between dust too small to notice and asteroids large enough to dominate headlines. This middle range is often where operational concern lives. Spacecraft are not threatened only by named near-Earth objects. They are also exposed to smaller populations that can still damage surfaces, instruments, windows, and thermal systems, especially outside the thicker protections close to Earth. Fireball records on Earth cannot measure every dangerous size class directly, but they can indicate whether the traffic in one part of the size and energy range appears to be behaving unusually. They can serve as an early sign that the background deserves renewed attention. That is the proper frame for reading a fireball database. It is neither a source of dramatic certainty nor a trivial collection of anecdotes. It is a patient observing system that gathers bright atmospheric entries over decades and asks whether the present resembles the past closely enough to be called ordinary. If the answer begins to look uncertain, then the record has already done something important. It has marked the moment when ordinary background conditions may no longer be comfortably assumed. Earth does not receive the debris environment in a raw state. Everything that arrives from interplanetary space must first pass through an atmosphere, and that atmosphere changes the event before any observer can measure it. This is the central limitation of fireball records and of nearly all ground-based impressions of meteoroid activity. The atmosphere protects life and softens the daily bombardment of the planet, but scientifically, it also acts as a filter, a transformer, and sometimes a source of confusion. A small object approaching Earth at cosmic speed does not simply fall through air the way a stone falls through still water. It encounters rapidly increasing resistance, compresses the gas in front of it, heats. That gas heats its own surface, sheds mass fragments, slows, and often disappears before reaching the ground. The visible streak that people call a meteor is not the object itself in any simple sense. It is the light produced by a violent interaction between fast-moving material and air. What reaches an observer is therefore already translated by physics before the human eye or a camera ever sees it. This makes inversion difficult. Inversion is the attempt to work backward from the observed light color duration, altitude, and terminal behavior to the original size, speed, strength, and composition of the incoming body. Scientists can do this to a degree, but the uncertainties remain large, especially when the observation comes from public reports rather than a dense instrument network. Two fireballs of similar brightness may arise from different combinations of mass and speed. A fragile body may flare brightly and break apart high in the atmosphere, while a denser one may penetrate deeper and generate sound farther down. The atmosphere can therefore make unequal objects appear similar, or make similar objects behave very differently. Even when the physics is well understood in principle, the practical measurement remains incomplete. Clouds intervene. Moonlight brightens the sky. City lights reduce contrast. The horizon obscures low events. Weather systems remove entire regions from observation for a night or for weeks at a time. Daylight hides events that would be striking in darkness. Oceans, deserts, forests, mountains and polar regions all carry their own observational gaps. Not because meteoroids avoid those places, but because people and cameras are less evenly distributed than the sky above them. This creates a second limitation beyond atmospheric filtering, the human geography of detection. Earth is large, but the reporting network is not uniform across its surface. It clusters where population is high, communication is easy, and public reporting systems are familiar. A bright event above a dense metropolitan corridor may produce hundreds or thousands of messages, while an equally energetic event above an empty stretch of ocean may pass with little more than a faint signature on a distant sensor, if any sensor happens to be operating there at all. This difference is not a small statistical inconvenience. It shapes the apparent record. The database reflects not only what arrives, but also where arrival intersects with human presence. Even over land detection changes with local habit and circumstance. People sleep. Curtains remain closed. Cloud decks move in overnight. Some observers look upward often, while most do not. Cameras point in other directions. Dash cameras, security cameras, and doorbell systems have increased accidental sky coverage in recent years, but they do so unevenly with strong biases toward roads, suburbs, and built environments. A long-term record must therefore account for a moving observer network, as much as for a moving meteoroid population. This is one reason raw increases in event counts cannot be accepted at face value. Improved detection technology can mimic physical change. More cameras create more chances to capture brief flashes. Faster internet sharing creates more chances that one observation leads to many reports. A bright event seen by a few people decades ago may have remained local memory. The same event now can become a regional record within minutes. The atmosphere introduces yet another asymmetry. Small incoming bodies are removed from the record entirely by burning up too high and too faint to attract notice. Medium bodies fragment unpredictably, scattering energy along a path that can look longer, brighter, or more complex than the original object would suggest. Large bodies that survive deeper may generate sonic booms and recoverable meteorites, but those are comparatively rare. The result is that the observable record emphasizes certain kinds of entrants and de-emphasizes others. It is not a census of everything that crosses Earth's path. It is a selective sample shaped by survival brightness timing and witness opportunity. In scientific terms, the selection function is severe. The atmosphere also converts a direct impact problem into an atmospheric light problem. On an airless world, an incoming object strikes the surface and deposits energy there. On Earth, much of that energy is spent aloft. This protects the ground, but it means that the event most people see is several steps removed from the original encounter. The fireball becomes a luminous consequence rather than a direct surface record. Acoustic reports are delayed because sound travels far more slowly than light. Persistent trains drift with high winds and change shape after the object has vanished. Fragmentation can produce multiple pulses that complicate eyewitness memory. By the time reports are written, perception has already edited the event. None of this makes ground observation worthless. It makes it conditional. Fireball databases remain valuable because they collect many imperfect signals and look for patterns large enough to survive those imperfections. Yet the limitations remain fundamental. Earth does not offer a clean viewing plane. It offers a protective, turbulent, inhabited shell through which the incoming flux is filtered before it is noticed. For that reason, any claim about a changing meteoroid environment must be made with restraint when it rests on atmospheric events alone. The sky over Earth provides evidence, but never the whole object in its untouched form. It provides signatures, traces, after effects, and glimpses shaped by airlight and the uneven map of human attention. The Moon offers a different kind of record. It does not transform incoming debris through air weather or the habits of observers on a crowded surface. It simply receives. In scientific terms, that simplicity gives it unusual value. An airless body preserves impact history more directly than a planet wrapped in atmosphere. And because the Moon travels through the same general near-Earth environment as Earth, it serves as a natural comparison surface for questions about meteoroid flux. Flux is the rate at which material passes through a given area over time. On Earth, that rate is partially hidden because the atmosphere destroys, slows, or alters a large fraction of incoming objects before they can be measured clearly. On the Moon, there is no such filter. A particle stone or small fragment that arrives on a collision path completes that path at the surface. It does not burn up into invisibility high overhead. It does not break apart in air and scatter its signal before impact. It strikes the regolith, the loose layer of dust and broken rock that covers much of the lunar surface and deposits its energy there. This alone changes the quality of the evidence. The Moon does not offer a report of interaction with air. It offers the result of direct impact. Over geological time, this has produced the most obvious feature of the lunar landscape, a surface written over by craters of many sizes. From the largest basins down to pits too small to notice, without instruments, the Moon preserves the long memory of bombardment. The record is not perfectly simple. Older surfaces can be covered by newer ejecta. Small craters can soften with time, and lighting conditions change what can be seen. Yet, compared with Earth, the preservation is extraordinary. There are no rivers to erase the mark, no vegetation to hide it, no plate tectonics to recycle the crust, no rain, wind, or ocean to blur the surface into a younger face. What arrives remains legible for far longer. This makes the Moon more than a neighboring world. It functions as a detector that has been exposed continuously to the same broad orbital neighborhood for billions of years. That continuity matters because a detector is most useful when it is unbiased in the most important ways. The Moon does not care whether the impact occurs above a city or an ocean. It does not care whether it happens at midday for one hemisphere of Earth or at midnight for another. Its surface does not depend on witness testimony, internet access, cloud cover, or seasonal observing campaigns. Impacts occur whether or not anyone watches, and the surface accumulates them without social amplification or demographic gaps. In that sense, the Moon behaves as a passive instrument, one that cannot choose where to look because it is always being looked at by events themselves. This is why comparisons between Earth-based fireball signals and lunar impact observations carry scientific weight. If Earth appears to be receiving more energetic atmospheric entries than usual, and the Moon also seems active under suitable viewing conditions, the combined picture becomes harder to dismiss as a quirk of human reporting alone. The Moon does not remove every uncertainty, but it removes several of the largest. It removes the atmospheric filter. It removes the translation from impact energy into atmospheric light. It removes the uneven map of human habitation as a determinant of whether an event enters the record. It also expands the size range of relevant incoming material, because even smaller bodies that would vanish in Earth's air can still strike the lunar surface and contribute to surface change. That difference must be handled carefully. Not every impact visible or measurable on the Moon corresponds neatly to a fireball category on Earth, because the same object would behave differently in different environments. Still, the Moon offers a cleaner reading of the incoming population than Earth can provide by itself. There is another reason the Moon serves as a valuable control case. Earth and Moon move through space together, separated by a modest cosmic distance compared with the scale of planetary orbits. They occupy nearly the same region of the inner solar system, and therefore sample much of the same background debris environment. They do not trace identical exposure at every moment, but they experience closely related conditions. This means that an unusual pattern seen in one may be examined against the other, not as a perfect mirror, but as a nearby companion record shaped by different physical rules. Earth gives atmospheric signatures. The Moon gives direct surface impacts. Together, they frame the same environment from opposite sides of a filter. The usefulness of the Moon becomes especially clear when considering small and medium debris populations. Large asteroids are often tracked individually, but smaller objects are far more numerous and much harder to catalogue in advance. Their cumulative behavior matters for risk for surface evolution, and for understanding whether a temporary cluster of events belongs to ordinary fluctuation or to a denser interval in the background population. The lunar surface receives this smaller traffic honestly. Every impact adds to the slow gardening of the regolith overturning grains, darkening some areas, brightening others, and constantly renewing the finest dust through countless tiny collisions. The surface is therefore not only a static archive of ancient impacts, it is an active record of ongoing bombardment. Even when no large crater forms, the surface continues to register the environment through pitting, churning, and flash events that may be seen under rare optical conditions. In this role, the Moon stands apart from the poetic image often assigned to it. It is not merely a bright object in the night sky. It is a nearby body continuously exposed to the same cosmic traffic that surrounds Earth, but without the atmospheric shield that complicates terrestrial evidence. That makes it one of the most valuable natural reference surfaces in planetary science. When the question concerns whether the near-Earth debris environment is behaving normally, the Moon becomes less a backdrop than a baseline, less an ornament of the sky, than a silent measuring surface whose great scientific strength lies in the fact that it simply lets impacts be impacts. The value of the Artemis II observation begins with geometry before it reaches interpretation. In space, what can be seen depends less on desire than on alignment, shadow, relative motion, and the simple fact of where one body stands in relation to another. The reported lunar flashes draw attention because they occur during a viewing arrangement that is unusually favorable for seeing the dark side of the Moon under high contrast. The mission trajectory carries Orion far beyond low Earth orbit and around the Moon, on a free return path, a route designed to send the spacecraft out into cislunar space and then bring it home without entering lunar orbit. Within that larger arc, there are periods when the spacecraft passes behind the Moon as seen from Earth. In ordinary public description, this phrase can sound like little more than a romantic location. Scientifically, it means that the spacecraft occupies a vantage point in which the Moon blocks direct view toward Earth, and where lighting conditions can become very different from anything available from the ground. During the relevant alignment, the Earth stands between the spacecraft and the Sun, producing an eclipse seen from behind the Moon. This is not the familiar experience of watching the Moon cross the face of the Sun from Earth's surface. It is the reverse geometry. From the spacecraft, Earth becomes the large occulting body, the object that blocks direct sunlight. Because Earth is much larger than the Moon, the shadowed interval can last far longer than a typical total solar eclipse seen on the ground. A surface observer on Earth usually sees totality for only a few minutes because the narrow shadow races across the planet. A spacecraft placed in the right cislunar position can remain within the alignment for much longer, not because the laws of eclipse change, but because the scale and relative motion of the system are different. What matters for the lunar surface is not only that the Sun is blocked, but that the optical environment becomes exceptionally clean. There is no atmosphere around the Moon to scatter light across the sky. There is no blue daylight to soften contrast, no clouds to brighten the horizon, no airglow to lay a luminous veil across the scene. When direct sunlight is removed from the line of sight and the dark hemisphere of the Moon lies exposed, the visual field becomes stark in a way that terrestrial experience rarely prepares for. The lunar night side does not vanish into featureless blackness. It remains faintly visible through earthshine, the sunlight reflected from Earth onto the Moon. This reflected light is weak compared with direct solar illumination, but it can be enough to define the broad dark disk and some large tonal differences across the surface. In such conditions, a brief flash on the lunar surface stands against a background that is dim but not absent. This balance matters. If the surface were fully invisible, a flash would have no spatial frame. If the surface were brightly lit, a moderate flash could be washed out. The eclipse geometry therefore creates a narrow but powerful observational window in which the dark hemisphere becomes visible at low brightness and sudden impact light can stand out sharply. Coverage also changes. From Earth, telescopic monitoring of lunar impact flashes is constrained by phase. Observers on the ground usually look for flashes on the dark portion of a crescent moon, when part of the night side is faintly lit by earthshine. Only a fraction of the lunar hemisphere is placed in that configuration at once, and even then the line of sight is influenced by sky brightness, weather, and the need to observe from the correct night-side phase angles. From a spacecraft behind the Moon during eclipse conditions, a much broader fraction of the lunar night side can fall within view at the same time. This does not make the spacecraft a magical detector, but it changes the viewing problem from a narrow sliver to a broad, dark face. In purely geometric terms, the monitored area becomes larger. That alone raises the chance that any ongoing impacts somewhere on the visible night side will be noticed. Yet geometry does not operate alone. Distance and human perception remain part of the event. Orion is not resting on the surface, but observing from far away, so each potential flash is compact and brief. The eye is less sensitive than dedicated electronic detectors to faint transient light, especially when the event lasts for only an instant. This means the favorable geometry helps by maximizing contrast and area, while human limitation works in the opposite direction by reducing sensitivity to weaker events. Both effects belong to the same observational setup. The eclipse does not erase that tension. It simply creates the rarest possible conditions under which the human eye has a chance to perceive a bright lunar impact directly. There is also a positional meaning to being behind the moon that extends beyond visibility. During that interval, the spacecraft experiences partial communication constraints and an unusual sense of separation from Earth, because the moon itself blocks the direct line between spacecraft and planet. Operational systems handle this through planned mission design, but observationally, the same separation underscores how uncommon the vantage is. It is not a standing platform for repeated monitoring. It is a transient corridor through space in which alignment, shadow, and line of sight briefly combine. That rarity is one reason the observation attracts such interest. The event does not emerge from a routine nightly survey using a purpose-built lunar impact observatory. It emerges from a mission whose path momentarily places human observers in one of the best natural positions for viewing the dark hemisphere under eclipse contrast. In that sense, the geometry is not background scenery to the report. It is the report's essential condition. Without the free return path, without the behind-the-moon interval, without Earth blocking direct sunlight, without the dark hemisphere lying in low Earthshine rather than bright day, there is no comparable naked eye opportunity. The significance of the position therefore lies first in what it allows to be seen. Only after that does any deeper interpretation begin. The reported flashes occupy a narrow space between observation and conclusion. NASA plans the Artemis II lunar flyby science window, in part around the chance to see impact flashes on the moon's darkened surface during eclipse conditions, and after the flyby, the agency states that the crew reports 6 light flashes created by meteoroids impacting the lunar surface. That statement is already significant on its own. It means the event passes from expectation into witnessed report. It does not yet mean that every physical detail of the impacts is settled. A lunar impact flash is the brief visible signal produced when a small natural object strikes the moon at cosmic speed and converts part of its kinetic energy into heat, melt, vapor, and light. Because the moon has no atmosphere, the incoming body does not burn away overhead as it would at Earth. It reaches the surface and releases its energy at the point of collision. For an instant, the impact site brightens. Material is shocked, heated, and ejected. Some fraction of that energy appears as a flash that can be detected if the geometry, contrast, and observing method are favorable. This is the physical basis of the event. The flash is real light from a real impact, not a reflection or a weather effect, because the moon offers no air, no cloud, and no ordinary atmospheric transient to imitate it. Yet once the flash is seen, a more difficult scientific problem begins. Brightness alone does not immediately yield a clean answer to the size of the impactor. The visible burst depends on the incoming speed, the angle of impact, the nature of the lunar surface, the composition and structure of the object, and the uncertain share of impact energy that is converted into visible light. In practical terms, one observed flash can be consistent with more than one physical combination of mass and velocity. A small but very fast particle can produce a noticeable burst. A somewhat larger but slower fragment may produce a similar apparent brightness. The event is therefore direct as an occurrence, but indirect as a measurement. Artemis II adds an additional layer to this complexity because the flashes are first reported by human observers rather than by a dedicated automated photometric system alone. That does not reduce their value. In some respects, it increases it because the crew occupies a rare vantage during a nearly hour-long eclipse with a mostly darkened moon in view. Still, the eye is not a calibrated detector. Human perception is strong at noticing contrast and sudden change, but weaker at assigning precise brightness duration or exact location in a way that removes later ambiguity. NASA's own description reflects this caution. After the report, scientists analyzed the downlinked images, audio, and other data in order to refine the timing and locations of the events and compare them with observations made by amateur astronomers on Earth. The sequence is important. First comes the report, then comes reconstruction, then, if possible, a more quantitative estimate follows. That order marks the difference between a striking witness account and a fully resolved scientific result. The number 6 therefore deserves two kinds of attention at once. It deserves attention because it is a concrete report from a highly unusual vantage in deep space. It also deserves restraint because 6 observations do not by themselves establish the full physical character of what is seen. The flashes are not yet 6 fully characterized impact solutions with precisely known masses, exact speeds, and confirmed crater coordinates. They are 6 reported light events on the dark lunar surface during an observing window intentionally designed to look for such phenomena. That distinction matters. It preserves the excitement of the observation without turning it into a stronger claim than the evidence presently supports. Even so, the scientific relevance remains substantial. NASA's lunar impact monitoring work treats impact flashes as a useful way to measure meteoroids in a size range that is otherwise difficult to capture with good statistical significance. The method is valuable precisely because the Moon receives these objects directly. In that framework, an eyewitness set of flashes from Artemis II is not a decorative side note to the eclipse. It belongs to an ongoing effort to understand the meteoroid environment near Earth and Moon and to assess possible hazards to future exploration on or around the lunar surface. The flashes matter because they represent impacts occurring in the same general neighborhood where future missions will operate. They also matter because they are seen under conditions that bring the dark lunar hemisphere into unusual clarity. What remains uncertain is not whether the crew reports seeing flashes. NASA confirms that they do. What remains uncertain is the complete physical interpretation of each event and whether the cluster taken by itself points to an environment that is merely observable in a rare way or temporarily more active than expected. Section by section, the story therefore remains disciplined here. The observation stands. The mechanism of impact flash formation is well understood in broad terms. The exact energies and sizes of these specific impactors remain matters for analysis rather than immediate declaration. In that careful middle ground, the 6 flashes become most interesting, not because they solve the larger question at once, but because they transform it from abstraction into something briefly unmistakably seen. What makes the 6 reported flashes scientifically difficult is not that they are impossible to imagine, but that 2 important effects pull in opposite directions at the same time. One effect increases the chance of seeing impacts. The other decreases it. If only one of those effects were present, the interpretation would be much easier. Together, they create a narrow zone of uncertainty in which the observation remains both plausible and striking. The first effect is coverage. From Earth, telescopic monitoring of lunar impact flashes usually takes place during crescent phases, when only a limited portion of the Moon's night side is visible, with enough Earthshine to define the surface while still keeping the scene dark enough for a flash to stand out. The watched area is therefore restricted by phase and perspective. A ground observer does not see the entire dark hemisphere at once under ideal contrast. A spacecraft placed behind the Moon during eclipse conditions sees a much broader spread of the lunar night side at the same moment. That difference matters in the mathematics of chance. If impacts are distributed approximately randomly over a much larger visible area, then the number of observable events should rise, even if the true underlying environment has not changed at all. More surface in view means more opportunities for a flash to occur somewhere within that view. This part of the problem is simple and must be granted in full. Any fair reading of the Artemis II report begins by acknowledging that the geometry alone should raise the expected count relative to an ordinary ground session. Yet the second effect moves the expectation in the other direction. The human eye is not as sensitive as a modern detector. A dedicated lunar monitoring system can integrate light record faint transients, compare frames, and recover events too subtle or too brief for unaided human vision. A person looking through a window, even under extraordinary contrast, remains limited by biology. Brief, faint flashes may fall below notice. Small differences in position, attention, and adaptation to darkness can determine whether an event registers at all. This means that while Artemis II enjoys a large coverage advantage, it also carries a sensitivity disadvantage. The crew may see only the brightest end of the impact distribution, not the full population of flashes that a calibrated instrument might record from the same vantage. Once both effects are recognized, interpretation becomes a balance rather than a verdict. Larger coverage pushes the expected count upward. Lower sensitivity pushes it downward. Whether those factors cancel each other, partially cancel, or leave a meaningful excess is not something that can be settled by intuition alone. It depends on the distribution of flash brightness across real lunar impacts, and that leads into one of the most uncertain quantities in the field. Scientists often refer to luminous efficiency when discussing impact flashes. This is the fraction of an impactor's kinetic energy that appears as visible light. If that fraction were known precisely then, a measured flash brightness could be translated more confidently into energy, and from energy into reasonable estimates of mass and velocity when combined with assumptions about impact speed. But luminous efficiency is not known with that level of certainty. It varies with impact conditions and is difficult to constrain because no laboratory setup perfectly reproduces a natural high-speed meteoroid impact on the lunar surface. Different impact angles target materials, incoming structures, and velocity regimes can all change how much energy becomes visible light, rather than heat shock vapor or excavation work in the regolith. The result is that back-calculating physical size from a flash remains subject to wide uncertainty. In practical terms, this uncertainty affects the baseline as well as the event itself. A baseline is only as strong as the model used to interpret it. If ground-based programs are counting flashes with detectors of known sensitivity, but the conversion from brightness to impact energy remains uncertain, then the true size distribution of incoming lunar impactors may not be pinned down as tightly as the count alone suggests. It is possible that Earth-based monitoring slightly underestimates how often impacts occur above the threshold visible to human observers under exceptional contrast. It is also possible that the 6 reported flashes are genuinely brighter than average and therefore represent a more energetic interval than the long-term baseline would normally imply. Both readings remain open because the bridge between observed light and physical event is not exact. This is why the report resists easy framing. It is not correct to treat 6 flashes as automatically impossible because the viewing geometry is far better than a routine ground campaign. It is also not correct to dismiss the report as nothing more than a larger field of view because naked eye sensitivity imposes a real penalty and should suppress marginal detections. The observation sits precisely in the middle ground where honest science often lives. It is neither self-explanatory nor easily ignored. Another difficulty lies in sample size. A single interval, even a memorable one, does not define a new norm. Random clustering can occur in any probabilistic environment. If many independent observing windows from comparable geometry were available, the 6-flash interval could be placed into a clearer distribution. But such windows are rare. The eclipse geometry, the mission path, the duration of totality, and the presence of trained observers all combine into an opportunity that does not repeat often. That rarity increases the value of the observation, but it also limits the strength of immediate statistical claims drawn from it. There is no large archive of equivalent human observations from the same vantage to compare against. The event, therefore, has high importance, but a thin comparative frame. In calm scientific terms, the proper conclusion at this stage is not that the baseline has been overturned and not that the baseline stands untouched. The proper conclusion is that the baseline is being tested by an unusual observation made under favorable yet imperfect conditions. That is enough to justify attention. It is also enough to justify restraint. The 6 flashes remain meaningful because they force both geometry and sensitivity into the same calculation, and once both are kept in view, the result becomes neither a simple anomaly nor a simple illusion, but a measurement problem still becoming clear. Around any mission that leaves low Earth orbit, the Sun becomes part of the operating environment in a more immediate way than it does for most human activity near the ground. It is always present as the source of light and heat for the inner solar system. But in spaceflight, it also becomes a changing physical influence whose behavior must be watched with care. This influence is often described under the broad term space weather. Space weather refers to changing conditions in space that arise from the Sun and move outward through the solar system, including variations in light magnetic structure and energetic particles. Some of these changes are gradual. The Sun follows a cycle of activity that rises and falls over about 11 years, with more sunspots, more active regions, and more eruptions near the higher part of that cycle. Other changes are sudden. A flare is a rapid release of energy from the Sun's atmosphere, usually associated with magnetic fields that become twisted and unstable. A coronal mass ejection is a large expulsion of plasma and magnetic field from the solar corona, the Sun's outer atmosphere. Solar energetic particles are high-speed charged particles that can be accelerated during flares or by shock waves driven through space by large eruptions. These different forms of activity do not all produce the same effects, and they do not always arrive at the same time. A flare can alter radio conditions and high-energy radiation almost at once because light travels quickly. A coronal mass ejection takes longer to move through interplanetary space. Energetic particles may arrive on still another timetable, depending on the structure of magnetic fields between Sun and spacecraft. For a crewed mission in cislunar space, this means the radiation background is not a single fixed number. It is an environment with a baseline and with possible episodes of temporary enhancement. That background matters because outside the deepest shelter of Earth's atmosphere and magnetic field, charged particles can interact more directly with spacecraft materials, electronics, and human bodies. Most of the time, the radiation environment remains within expected bounds for mission planning, but expectation does not mean indifference. Mission Control and Space Weather Centers watch the Sun continuously, because the physical state of the solar atmosphere can change in ways that affect operations, caution levels, and onboard procedures. During a period of elevated solar activity, the meaning of an active Sun must be handled precisely. Increased activity does not automatically mean a severe radiation event for every spacecraft. The Sun can produce many active regions and many modest flares without creating a major particle storm at a specific location. The geometry matters. The size of the eruption matters. The magnetic connection between the eruption site and the spacecraft matters. A bright event on the Sun may look dramatic in images, yet produce only limited operational consequence at a given point in space. At the same time, a more modest-looking event can still matter if the particle environment rises enough to increase crew exposure or affect instruments. This is why disciplined language is important. Solar conditions may be elevated, unsettled, or closely monitored without implying immediate crisis. In scientific terms, the solar environment during a mission is described through measured quantities such as particle flux, X-ray output, proton levels, and the state of interplanetary magnetic fields. These quantities turn a bright star into an operating variable. For Artemis-class missions, the concern is not only what the Sun looks like, but what it is doing physically across the region the spacecraft is crossing. The corona is central to this picture. The corona is the Sun's extended outer atmosphere, a tenuous region of hot plasma structured by magnetic fields. It is far less bright than the visible solar disk, which is why it is usually hidden, except during eclipses or with special instruments. Yet, it is from this extended atmosphere that the solar wind flows outward, carrying charged particles and magnetic structure into the inner solar system. When the corona is relatively quiet, the solar wind still persists as a constant stream. When magnetic fields become disturbed, the corona can release matter and energy in larger outbursts that reshape conditions far from the Sun itself. In this sense, the Sun is not only a distant light source for the mission, it is the engine that fills interplanetary space with a moving plasma environment. A spacecraft traveling beyond low Earth orbit moves through that environment, rather than remaining under the thicker shelter of terrestrial conditions. The practical meaning of this is calm but important. Crew planners consider shelter procedures, monitoring methods, and mission timing, with the understanding that solar activity can add a temporary layer of risk to a voyage that is otherwise shaped by propulsion guidance and thermal design. Solar conditions do not explain every unusual thing that happens in near-Earth space, and they must not be used as a convenient answer for unrelated events. In particular, solar activity is not a known direct cause of sudden changes in meteoroid population density. The two subjects belong to the same mission context, but they are different physical domains. One concerns charged particles, magnetic fields, and radiation. The other concerns natural, solid bodies moving on orbital paths. They may coexist in the same week or during the same flight, without being causally linked. That distinction matters because a complex mission can gather public attention around several simultaneous phenomena that are physically separate. The role of this section is therefore narrower. It places the mission within the changing radiative and magnetic environment created by the Sun and shows why elevated solar conditions deserve careful monitoring during cislunar travel. It does not claim that solar variability answers the larger debris question. It only establishes that the mission unfolds under a star whose output is never perfectly constant, and that any passage beyond low Earth orbit carries the crew into a region where those changes matter more directly than they do below the sky. Leaving low Earth orbit changes the meaning of exposure. Near Earth, spacecraft still move in space, but much of their environment is shaped by the presence of the planet itself. Earth does not simply provide gravity, visual reference, and a destination below. It also provides shielding. That shielding takes two main forms. One is the atmosphere, a deep column of gas that absorbs a large share of incoming energetic radiation before it can reach the surface. The other is the magnetosphere, the broad magnetic structure generated by Earth's interior and shaped by the solar wind. The magnetosphere does not form a perfect wall, but it deflects and channels many charged particles, creating a region of partial protection around the planet. Spacecraft in low Earth orbit remain inside much of that magnetic influence for most of their mission time. They are not free from radiation. They still pass through an environment that includes trapped particles, cosmic rays, and occasional solar effects. Yet they operate within a zone where Earth continues to alter what arrives. A mission traveling to lunar distance leaves that condition behind. It enters cislunar space, the region between Earth and Moon, where the geometry of protection becomes thinner, more variable, and at times largely absent. In this region, the spacecraft no longer circles safely inside a deep magnetic cocoon for every hour of flight. It moves outward through zones where Earth's magnetic field weakens with distance and where direct exposure to the interplanetary environment becomes more complete. That difference is quiet in appearance, but significant in physics. The spacecraft may still look serene against black space, with only the Sun, Earth, and Moon providing the obvious visual structure of the scene. Yet the invisible environment around it has changed. Charged particles can arrive with less interference from the protective structures that surround the planet. Galactic cosmic rays, which are high-energy particles arriving from outside the solar system, remain part of the background throughout space. Solar particles, when present, also move through this region with fewer barriers than they face closer to Earth. The result is not a constant emergency, but a higher baseline importance of radiation awareness. In low Earth orbit, a crew lives in space while still benefiting from Earth's lingering defenses. On a cislunar path, the crew begins to travel beyond them. The distinction is essential because human bodies and spacecraft systems respond to radiation in cumulative and event-based ways. A cumulative dose builds gradually over time from constant background exposure. A short event dose can rise more quickly if solar activity temporarily enhances the local particle environment. Mission planners therefore do not treat deep space travel as merely a longer version of orbital flight. The basic mechanics of propulsion and navigation may share common roots, but the environmental context becomes different enough to require its own planning logic. This includes monitoring solar conditions, modeling expected exposure, assigning shelter procedures, and understanding which parts of the spacecraft provide more mass between crew and incoming particles. In radiation protection, mass matters because material can absorb or slow some kinds of radiation, though not all forms are stopped equally well, and some interactions can create additional secondary particles. This is why shielding is never a simple on or off condition. It is a matter of degree, geometry, composition, and energy. Orion carries the crew through a mission profile that crosses this boundary from greater terrestrial protection to lesser terrestrial protection. The spacecraft becomes, in practical terms, the primary shelter once Earth's atmospheric and magnetic advantages fade. That does not mean the vehicle is fragile or unprepared. It means the scale of dependence changes. Near Earth, the planet and the vehicle share the job of protection. Farther out, the vehicle does more of that work by itself. This shift also affects how mission risk is communicated. Public imagination often associates space danger with visible objects, such as asteroids, or with dramatic launch and landing phases. Radiation is different. It is invisible, statistical, and strongly dependent on timing. A perfectly smooth day in visual terms can still belong to an elevated particle environment. A week of solar images that appears active may still produce manageable exposure if the geometry and particle output remain favorable. Risk in this regime is therefore not read from appearance. It is measured, modeled, and watched. The Van Allen belts illustrate this change in protective context in a particularly clear way. These belts are regions of trapped charged particles held by Earth's magnetic field. Spacecraft traveling beyond low Earth orbit must cross them, but the crossing is managed through trajectory design and limited transit time. The belts themselves show that Earth's magnetic environment is not a simple dome of safety. It is a structured region that can both protect and concentrate particles depending on location. Once beyond that system, the spacecraft enters a different balance in which trapped terrestrial populations matter less, and the open interplanetary background matters more. Cislunar travel therefore represents a threshold, not because everything suddenly becomes extreme at one precise line, but because the dominant environmental frame shifts. There is another aspect to leaving the magnetosphere that matters for interpretation of unusual mission timing. When several notable space conditions occur near the same mission window, public discussion can easily fold them into a single dramatic narrative. A close asteroid passage, a period of active solar conditions reported lunar impact flashes, and concerns about re-entry safety may seem like one layered crisis simply because they share a calendar. In physical terms, however, the crew's passage beyond Earth's protective reach gives each of those subjects a sharper practical edge without proving that they are causally linked. The deeper significance of the route is simpler and more disciplined. Artemis II carries human beings into a region where Earth no longer softens the environment to the same extent. The mission, therefore, revives a condition not experienced by astronauts, since the Apollo era sustained travel through deep space beyond low Earth orbit, where the spacecraft is no longer merely a vehicle moving above the planet, but the main inhabited barrier between the crew and the wider physical reality of the inner solar system. A close asteroid flyby belongs to a different category of event than a broad shift in the near-Earth meteoroid environment, even when the two happen to appear in the same week and inside the same public story. The distinction begins with orbit. A catalogued near-Earth asteroid is an individual body on a calculable path. It may be newly discovered, its uncertainties may still be shrinking as more observations arrive, and its future encounters may carry some non-zero statistical probability on long timescales, but at the moment of a close pass, it is still one object following one trajectory. A background meteoroid environment is something else entirely. It is not a single body, but a population made of many fragments with many sizes, many source histories, and many slightly different paths through the inner solar system. When public attention hears that an asteroid will pass closer than the Moon, the phrase can sound as if a large stone is entering the same category as an elevated debris background, or as if closeness itself proves physical linkage with other unusual observations. In practice, closeness proves only geometry. It tells how near the object will come to Earth in distance, not whether it shares an origin with an observed fireball cluster or with reported impacts on the Moon. During this mission window, one notable case is Asteroid 2026 GGD, a near-Earth object classified in NASA's Small Body Database as an Apollo asteroid. Reports on April 9th describe it as roughly 16 meters in diameter, passing Earth at about 250,000 kilometers, or about 0.65 lunar distances, with a later approach even closer to the Moon, while posing no threat to either body during that encounter. NASA's Asteroid Watch dashboard gives the average Earth-Moon distance as about 385,000 kilometers, which is why a pass like this is correctly described as sub-lunar distance. But the same dashboard also emphasizes that many objects make relatively close approaches on astronomical terms without being dangerous impacts. The phrase "closer than the Moon" therefore needs careful handling. It sounds extreme because the Moon is humanity's familiar unit of nearby space, yet on the scale of orbital mechanics, it remains a measure of passing distance, not a forecast of collision. A small object can pass inside that distance safely if its trajectory and timing do not intersect Earth's position. The public mind often imagines space as crowded only when a named object arrives, but orbital science works in a more orderly way. Most close approaches are misses by definition, and the purpose of planetary defense tracking is to know which misses are clean misses, which ones require more observation, and which ones merit long-term statistical attention. This is why a close flyby can feel dramatic while remaining operationally ordinary for astronomers who watch such things daily. The interest lies in detection, orbit refinement, and characterization, not in assuming that every near pass is part of a wider physical disturbance. That caution becomes especially important when a mission like Artemis II is underway, because several independently interesting conditions can overlap in calendar time and create the impression of a single mounting pattern. A crude lunar flyby reported impact flashes on the Moon active solar monitoring, and a small asteroid passing inside lunar distance can seem like connected pieces because they are narrated together. Yet physical connection requires more than simultaneity. It requires a plausible dynamical link. For an individual asteroid to explain a rise in fireball reports or a cluster of small lunar impacts, there would need to be evidence that it is shedding material into Earth-crossing space in a way that matches the timing geometry and distribution of those other events. In the absence of such evidence, the safer interpretation is separation. One object passing near Earth is one orbital fact. A possible change in the background debris environment is a different question. The two can coexist without one causing the other. In some ways, the asteroid flyby can even mislead by scale. A body around 16 meters across is large enough to draw headlines and small enough to pass unnoticed by the naked eye. But the meteoroid environment relevant to atmospheric fireballs and many lunar impact flashes often involves a broad size range extending far below that level. The physics of a named close-approach asteroid is therefore not automatically the physics of the background population. One belongs to tracked near-Earth objects. The other belongs to distributed debris. Both matter, but they matter differently. The asteroid belongs to planetary defense and orbital prediction. The background belongs to flux statistics and environmental exposure. Keeping those categories separate is part of responsible interpretation. The most accurate way to place the flyby within this mission period is to say that it sharpens awareness without settling the larger question. It reminds observers that Earth and Moon move through a region where natural bodies of many sizes cross nearby space. It demonstrates that sub-lunar flybys are real and measurable. It reinforces the value of tracking systems that identify objects shortly before close approach and confirm that they are safe. It does not by itself prove that the broader near-Earth environment has changed. In calm scientific terms, the flyby is best read as context rather than cause, as a vivid example of orbital proximity rather than evidence of a hidden common signal tying every unusual event together. When that distinction is kept intact, the story becomes clearer. A close asteroid approach can be genuinely notable and still remain separate from the question of whether the quieter background traffic of small debris has become denser than before. Returning from lunar distance is not the same problem as returning from low Earth orbit with a familiar capsule and a practiced sequence of parachutes. The shape of the spacecraft may look similar from the outside, and the final image of splashdown may resemble earlier missions, but the physics of the descent begins from a very different state. A vehicle falling home from low Earth orbit starts with less energy relative to Earth than a vehicle returning from the Moon. Energy here means not only height above the planet, but motion. A spacecraft coming back from lunar distance approaches Earth with far greater entry speed. And because aerodynamic heating rises sharply with speed, the difference is not a matter of a little more heat or a little less margin. It is a different re-entry regime. NASA describes Orion's return from lunar missions as a high-energy entry that requires a skip entry profile. And for Artemis II, the agency says the spacecraft will reach the upper atmosphere traveling nearly 35 times the speed of sound before beginning a planned communications blackout as plasma builds around the capsule. That description captures the essential fact. The spacecraft does not simply descend through air. It arrives carrying so much speed that the atmosphere itself becomes an extreme part of the engineering problem. The heat seen during such an entry is not caused by simple friction in the ordinary sense used for objects sliding across surfaces. It comes mainly from compression. As Orion forces its way into the upper atmosphere at hypersonic speed, the gas ahead of it cannot move aside gently. It is compressed and heated intensely, forming a sheath of very hot ionized gas around the vehicle. This plasma radiates heat toward the spacecraft and interferes with communications, which is why blackout is expected during the most intense part of the descent. The capsule must survive not only high temperature, but the combined effects of heat flux pressure, turbulence, and timing. Entry angle matters greatly. Too steep, and the loads and heating rise too quickly. Too shallow, and the spacecraft can skip away in the wrong way or travel too far before it loses enough speed. Lunar return, therefore, demands more than a strong shell. It demands precise guidance through a narrow corridor of acceptable conditions. This is where the distinction between a direct fall and a skip entry becomes important. In Orion's design, skip entry means the capsule first dips into the upper atmosphere, uses drag and lift to shed part of its energy, then exits the densest part of that first encounter before descending again for the final entry and parachute phase. NASA explains that this technique extends range and reduces the rate of heating by splitting the event into two major heating episodes rather than one single deeper plunge. In other words, the atmosphere becomes not only a barrier, but a shaped path, something the spacecraft briefly uses as part of its return, rather than merely enduring all at once. That path must be calculated carefully, because the capsule is neither an airplane nor a simple falling object. It generates modest aerodynamic lift because of its shape and orientation, and that lift allows guidance during entry, but only within tight physical limits. The problem is therefore one of controlled surrender to the atmosphere. The spacecraft must yield enough speed to survive, maintain the correct attitude, so the heat shield stays where it belongs, and continue toward a recovery zone after blackout ends and parachute deployment becomes possible. The final moments of the descent can look almost gentle in public imagery. Drogue parachutes open high above the ocean. Main parachutes follow. The capsule settles into splashdown. Yet that calm ending depends on a much harsher process just minutes earlier, when the vehicle is still wrapped in plasma and the heat shield is doing the essential work of keeping interior conditions survivable. Orion's shield uses an ablative material called AVCoat. Ablation means that the material is designed to char, erode, and carry heat away in a controlled manner, rather than simply remaining unchanged under extreme temperature. This logic has deep roots in lunar return design, going back to Apollo. But the modern vehicle is not a duplicate of earlier spacecraft. It has its own geometry, manufacturing methods, and performance envelope, which is why real flight data matters so much. The practical difference between low Earth orbit return and lunar return can therefore be summarized in a quiet but important way. In low Earth orbit re-entry is serious and technically demanding, but it occurs from a lower energy starting point and within a mission class long practiced by many crews. From lunar distance, re-entry becomes one of the defining events of the entire mission because the vehicle comes home carrying deep space speed that must be shed through a carefully managed atmospheric encounter. The heat shield is not just one subsystem among many during that phase. It is the barrier that makes the return physically possible. So when mission planners and engineers speak carefully about re-entry from the Moon, they are not adding unnecessary drama. They are describing a genuine threshold in human spaceflight, the moment when a spacecraft that has traveled far beyond low Earth orbit must turn all of that outward journey back into survivable motion through the air above the Pacific. After Artemis I returned from its uncrewed journey around the Moon, the heat shield became one of the most closely examined parts of the entire spacecraft. During flight, Orion survives re-entry and protects the crew module as intended. Yet post-flight inspection shows that parts of the ablative surface have behaved differently from pre-flight predictions. The shield is covered with AVCoat, an ablative material designed to absorb and carry away heat by charring, eroding, and venting gases as the outer layer responds to the thermal loads of return from lunar distance. In principle, this is not a failure mode, but the normal logic of the system. The shield is meant to change during entry. It is not built to remain pristine. What matters is whether it changes in the expected way and whether enough protective margin remains throughout the heating pulse. Artemis I reveals that in several locations, the outer charred layer does not simply wear away smoothly. Instead, pressure develops beneath parts of that layer. Cracking occurs, and pieces of charred material break away more unevenly than engineers had predicted before flight. The distinction is subtle but important. The heat shield does not collapse, and the spacecraft interior does not approach unsafe temperatures. NASA later states that if a crew had been aboard Artemis I, they would have remained safe, and that internal cabin temperatures stay well within limits during the mission's return. At the same time, the discrepancy between expected and observed behavior cannot be treated as a small cosmetic matter, because crewed lunar return depends on confidence, not only that the system works once, but that engineers understand precisely why it works and where the margins truly lie. This is the lesson phase of a test campaign. An early mission is valuable not because it proves every model perfect, but because it exposes where reality and prediction do not fully coincide. NASA's investigation eventually identifies a specific physical cause. During Artemis I's skip entry return, Orion experiences two major atmospheric encounters, separated by a brief period of reduced heating between dips. That detail turns out to matter. According to NASA, the lower heating rates seen in flight during this skip profile allow thermal energy to build within the avcoat, while gases generated by ablation do not vent and dissipate as expected. The issue is tied to permeability, which in this context means the ability of the charred material to let gases pass through it. In regions where the avcoat does not become sufficiently permeable under the actual flight heating conditions, internal gas pressure can build beneath the char layer. That pressure then contributes to cracking and uneven shedding of the outer material. In other words, the problem is not that gases are unexpectedly created. Gas generation is part of normal ablation. The problem is that, under the measured Artemis I environment, some of that gas cannot escape efficiently enough through the char layer at the necessary time. NASA further explains that ground tests before flight had reproduced the skip phenomenon, but at higher heating rates than Orion actually experiences in flight. Under those more severe test conditions, the char becomes permeable and ablates in a way that lets pressure vent as expected. Under the less severe but still mission-realistic Artemis I re-entry environment, the progression is different. Char formation slows while gas still forms within the layer, allowing pressure to rise. This finding changes the engineering understanding of what the real entry environment does to the material. It shows that the most relevant condition is not simply maximum heating in isolation, but the specific time history of heating and cooling associated with a lunar skip return. The investigation is extensive because the consequence of misunderstanding would be serious. NASA reviews flight imagery and sensor data and removes about 200 avcoat samples from the flown heat shield for inspection and analysis. The agency also conducts 121 individual tests across multiple post-flight thermal campaigns and uses upgraded arc jet facilities to reproduce the measured environment more accurately. That reproduction matters because an engineering explanation is most persuasive when the observed behavior can be recreated on the ground under the right conditions. NASA reports that the enhanced testing is able to demonstrate the cracking behavior seen after flight, supporting the conclusion that gas pressure buildup in insufficiently permeable avcoat is the root cause of the unexpected char loss. Additional evidence strengthens the interpretation. Areas identified as permeable before flight do not show the same cracking and char loss, suggesting that permeability is indeed the key parameter separating stable venting from pressure buildup. NASA's independent review team later agrees with the agency's technical findings, which adds confidence that the explanation rests on more than internal preference or convenient modeling. The broader lesson is not only about one heat shield on one mission. It is about how modern lunar return vehicles must be tested against the true thermal history they will actually experience, not merely against simplified or more intense cases that seem conservatively severe. A less extreme heating rate can in some circumstances produce a more troublesome internal response if the material's venting behavior depends on how that heating evolves over time. That is a quiet but important engineering lesson. Severe does not always mean most revealing. Sometimes the real flight profile exposes the more relevant behavior. Artemis I, therefore, teaches two truths at once. First, Orion's shield works well enough to protect the spacecraft through actual lunar return, with internal thermal performance exceeding expectations. Second, the detailed physical behavior of the shield differs from what engineers expect, and that difference is significant enough that NASA must fully understand it before sending crew. The purpose of the investigation is not to dramatize a failure, but to convert a surprising post-flight condition into a resolved engineering problem. By the time Artemis II approaches launch, the heat shield is no longer treated as an unexplained anomaly. It is treated as a system whose behavior has been traced to gas transport permeability, cracking, and char loss under a specific skip entry environment, and therefore as a system that now requires informed decisions rather than hopeful assumptions. NASA's forward path for Artemis II does not begin by pretending the Artemis I heat shield behavior never happened. It begins by changing the return in a way meant to avoid spending as much time in the thermal conditions that produce the troublesome material response. That distinction matters because the agency does not announce a new heat shield for Artemis II. Instead, it states that the current shield already attached to Orion can safely support the crewed test flight when paired with a modified atmospheric entry trajectory. Specifically, NASA says engineers will shorten how far Orion can travel between first entry into Earth's atmosphere and splashdown in the Pacific, thereby limiting how long the spacecraft remains in the temperature range associated with the Artemis I char loss phenomenon. NASA also states that the skip entry concept remains necessary for return from lunar missions, because those missions come home at higher speeds than the crewed lunar landing returns planned later in the campaign, and that future shields for lunar landing missions are being manufactured with changes intended to produce more uniform and consistent permeability. The logic of the Artemis II change is therefore not to remove complexity from re-entry, but to reshape timing within that complexity. A skip entry still uses the atmosphere in stages to shed energy, but the path within that method can be adjusted so the vehicle does not linger as long inside the range, where gases in the avcoat are more likely to accumulate pressure beneath a char layer that has not yet become permeable enough to vent them efficiently. In quiet engineering terms, NASA is treating the issue as a trajectory material interaction problem. The heat shield and the path through the atmosphere are not independent variables. The material does not respond only to peak severity. It responds to the history of heating over time. Once Artemis I shows that the relevant risk lies in how the material behaves during a specific part of the thermal profile, the corrective action naturally shifts toward altering that profile where possible. This is why the agency's chosen fix sounds modest in words, but substantial in meaning. A shorter flight distance between atmospheric interface and splashdown is not simply a navigational convenience. It is a way of changing how long the vehicle remains inside the thermal regime that matters most to the shield's response. The practical meaning is that Artemis II will not be a pure repetition of the Artemis I return. It will still be a lunar speed entry, still a hypersonic encounter, still a mission that depends on ablative protection and careful guidance. But the heating history will be intentionally reshaped to reduce time spent in the problematic zone. That is how test flight lessons mature into mission rules. NASA's public language around this point is careful, and that care is worth preserving. The agency does not say the previous phenomenon becomes impossible. It says the trajectory modification limits how long Orion remains in the relevant range, and that extensive investigation gives engineers confidence the current shield can safely fly the Artemis II crew. Confidence here is not casual belief. It rests on post-flight samples, recreated test environments, and the finding that the material response can be better managed by changing the entry conditions the capsule experiences. This is also why the forward path divides the Artemis program into two different thermal protection situations. Artemis II uses the shield already attached to the spacecraft because schedule, manufacturing state, and the revised trajectory combine to support that choice. Artemis III and later lunar landing returns draw on manufacturing enhancements informed by the investigation, especially the need for consistent permeability across the heat shield material. That division shows a program learning on two timescales at once. One timescale is immediate and operational. Make Artemis II safe with the hardware in hand by adjusting the return conditions. The other is longer and more structural. Improve how future heat shields are built so that material behavior remains more uniform across the more demanding family of returns still to come. The revised re-entry strategy therefore belongs to a broader tradition in flight test logic. Early missions are not only demonstrations of existing design strength. They are opportunities to identify where the system behaves differently than expected, and then to decide whether the better response is redesign, operational constraint, or some mixture of both. In this case, NASA chooses a mixture, but for Artemis II, the visible part is operational. The mission returns through a trajectory designed to reduce time in the range that drives gas pressure buildup and char cracking. That is a disciplined response because it addresses the specific physics revealed by flight, rather than treating the issue as a vague need for more safety margin in the abstract. It also preserves the purpose of Artemis II as a crewed test flight. The mission is not yet the full landing architecture of later expeditions. It is intended to prove that Orion and its systems can carry people around the Moon and back in the real environment of deep space. A revised re-entry that keeps the test within a better understood thermal envelope fits that role. It does not erase risk, because no lunar return can erase risk, but it narrows the uncertainty to a form NASA believes is acceptable for a crewed mission. This is the deeper meaning of the revised strategy. The path home is no longer just the mathematically available path. It becomes the path selected after the first full-scale lunar return teaches the program that material response depends on more than total heat load. It depends on sequence duration and the exact way the atmosphere is used to bleed off deep space speed. Artemis II therefore comes home through a re-entry not simplified, but informed. The atmosphere remains severe, the plasma blackout remains expected, the speed remains immense, and the heat shield remains central. Yet the return has been adjusted so that the most important lesson from Artemis I is carried forward, not as a warning left hanging in uncertainty, but as a trajectory decision written directly into the mission itself. At this stage of the story, the available evidence supports two readings at once, and the discipline of the analysis depends on holding both without allowing either one to become more certain than the data permits. The more conservative reading begins with the principle that unusual clustering does not automatically imply unusual physics. The near-Earth environment is variable by nature. Fireball counts fluctuate. Observation quality changes. Public reporting networks expand. Viewing geometry can turn an ordinarily invisible process into a suddenly memorable one. Under this reading, the first quarter fireball signal recorded by the American Meteor Society deserves notice but remains vulnerable to residual observational bias even after statistical correction for the growth of the reporting network. NASA's confirmation that Artemis II is positioned during eclipse conditions to observe possible impact flashes on the lunar dark side means that seeing flashes is itself an anticipated scientific opportunity, not an inherently impossible surprise. The broad night-side coverage from Orion's position naturally increases the chance of witnessing impacts somewhere on the visible hemisphere, while the lack of a large archive of directly comparable human observations from the same vantage makes it difficult to say exactly how unusual 6 reported flashes truly are as a rate rather than as an impression. Under this conservative interpretation, the close passage of Asteroid 2026 GD and the period of elevated solar monitoring belong to the same calendar, but not necessarily to the same physical chain. NASA states that the asteroid poses no threat during its approach, and solar activity remains a separate environmental concern, rather than a known cause of changes in meteoroid density. The re-entry issue also stands in its own engineering category. NASA's post-Artemis I investigation identifies the cause of unexpected char loss and reports that the Artemis II trajectory has been adjusted so the current shield can safely support the crewed mission. In this reading, the public narrative feels densely packed because several notable spaceflight conditions happen at once, but the underlying reality may still be ordinary in the statistical sense. A rare mission sees the Moon under rare lighting. A long-running database produces a temporarily strong signal that may settle back toward baseline with more months of data. A tracked asteroid passes close, yet harmlessly. A heat shield concern is converted into a managed engineering constraint. The impression of convergence is real, but convergence of headlines is not the same as convergence of causes. It is also possible, under this reading, that the deepest lesson of the episode will concern measurement itself. Ground observers may now be better at noticing energetic fireballs than they were only a few years earlier, while a human crew in cislunar space may for once have occupied an angle from which ordinary lunar impact activity becomes visible in a way that earlier generations rarely had the chance to see. The more consequential reading begins from a different emphasis. It accepts the same need for caution, but assigns greater weight to the independence of the signals. In that interpretation, the American Meteor Society result matters precisely because the anomaly is reported as surviving correction for growth in the observer network, and because it is not described only as more reports, but as more energetic and more widely witnessed events associated with a known sporadic source region, rather than a single obvious one-off cause. The Artemis II flashes matter not because they prove a new environment on their own, but because they arise from a detector that does not share Earth's atmospheric filter or its uneven human geography. The Moon receives incoming material directly, and an observation from a rare eclipse geometry therefore becomes more than a dramatic anecdote. It becomes an independent glimpse into the same neighborhood of space sampled by Earth, but without several of Earth's largest distortions. The asteroid flyby does not prove a connection, yet it reinforces the simple fact that Earth and Moon continue to move through a region crowded enough with natural bodies that sublunar passes are part of the real operating context, not abstract textbook possibility. The solar backdrop also sharpens rather than explains the moment. It places the mission in a period when the wider space environment already demands close monitoring, increasing the practical seriousness of any voyage beyond the magnetosphere. The re-entry issue deepens this consequential reading in a quieter way. NASA's confidence in the revised return is grounded in testing and engineering analysis. But the very existence of that redesign reminds the observer that Artemis II is not occurring inside a routine, fully domesticated environment. It is a mission operating at the edge of what human spacecraft currently do a deep space crewed flight through a variable debris field under an active sun, with real material limits written into the return profile. In this reading, the convergence is not proof of a single hidden cause, but it is still meaningful. It suggests that the ordinary background state of near-Earth space may be less comfortably ordinary than earlier assumptions imply, and that the first task of science is now to decide whether recent observations are exposing a temporary surge, a measurement improvement, or a baseline that has been underestimated for years. It also gives greater weight to the possibility that several imperfect instruments, each with different biases, are nevertheless beginning to lean in the same direction, and that such alignment can sometimes matter before certainty arrives. Neither interpretation wins outright within the current evidence. The conservative view is stronger wherever the data remain thin, especially around sample size and comparability. The consequential view is stronger wherever independent observations seem to point in the same direction without sharing the same main biases. The scientific position for now is not a compromise for the sake of comfort. It is a deliberate suspension between two live possibilities, one of which says that a rare mission has illuminated familiar processes under rare conditions, and the other of which says that rare conditions have briefly revealed that the familiar processes themselves may be changing in ways only now becoming visible. What the near-Earth environment is telling at this point is not a complete answer, but a disciplined pattern of partial answers. It says first that the background around Earth and Moon is not a static emptiness, but an active field of natural debris, whose ordinary state must be measured statistically rather than assumed from appearance. It says second that the recent fireball record on Earth has become difficult to dismiss as mere anecdote, because the American Meteor Society reports that the first quarter of 2026 shows a rise in large fireball events above the recent average, even after accounting for the expanding observer network, while also noting that the total number of fireballs remains closer to normal and that the strongest signal may lie in the size distribution of the objects being noticed rather than in a universal rise across every category. That combination matters because it narrows the claim. It does not say that all incoming material has suddenly surged. It suggests instead that the more energetic part of the visible atmospheric sample may have shifted in a way that deserves sustained watchfulness and additional comparison with other detectors. In scientific language, that is already meaningful. A background environment does not need to become globally extreme in every size class to change the operational picture for observers, spacecraft, or surface hazard assessment. It only needs to move enough in the relevant range to alter the probabilities of noteworthy events. At the same time, the environment is also saying that Earth alone is not a sufficient judge of its own exposure. The atmosphere still filters, brightens, hides, and reshapes what arrives, and the map of witnesses remains uneven across oceans, daylight zones, and lightly populated regions. For that reason, the strongest conclusions cannot come from terrestrial fireball reports by themselves, however valuable those reports may be. They need comparison with cleaner surfaces and rarer vantage points. This is where Artemis II becomes scientifically important in a way that exceeds the drama of a single mission moment. NASA states that the crew uses the Eclipse viewing opportunity to watch for flashes from meteoroids striking the Moon, and later reports that the crew witnesses 6 such flashes during the lunar flyby. The importance of that report lies not only in the number itself, but in where the observers are and what the Moon represents. The crew is not watching through air. The Moon is not filtering the incoming bodies through atmosphere. The observation therefore belongs to a surface that receives impacts directly and to a geometry that opens an unusually large high-contrast view of the lunar night side. That does not erase uncertainty. Human eyes are not calibrated photometers, and the relation between flash brightness and impact energy remains imperfectly constrained. Yet the observation still matters because it comes from a natural control surface in the same broad neighborhood of space sampled by Earth, but without several of Earth's strongest biases. In quiet terms, Artemis II does not settle the case. It improves the case by adding a rarer kind of evidence to it. The environment is also saying something about the value of patience. One remarkable interval is not yet a new baseline. One mission window is not a climatology of cislunar space. A true shift in the near-Earth debris environment would need support across continued records, repeated observing opportunities, and careful comparison between atmospheric events, lunar detections, and orbital models of known source populations. This means the correct posture remains neither alarm nor dismissal. It remains structured attention. The present evidence is strong enough to justify that attention because independent lines of observation now touch the same broad question without sharing the same main distortions. The present evidence is also incomplete enough to forbid any claim that the larger puzzle is already solved. That balance is the mature scientific message. The environment may be revealing a temporary enhancement, a more concentrated stream within the ordinary sporadic background, or a baseline that earlier observing methods have sampled less completely than assumed. It remains uncertain which of those readings will stand when more months of data accumulate. What is no longer uncertain is that the question itself is now better formed than before. Before this mission period, the issue could still be framed as an impression drawn from scattered atmospheric events. After the fireball analysis and the Artemis II lunar flyby report, it becomes a sharper inquiry about whether multiple observing systems are beginning to register the same underlying reality from different sides of the same space. In that sense, the near-Earth environment is telling a simple but important truth. It is telling that ordinary space is never truly ordinary, that a quiet background can still carry structure, and that rare human presence beyond low Earth orbit can sometimes illuminate that structure in ways instruments near the ground cannot easily match. Artemis II matters because it places trained observers at lunar distance in eclipse geometry inside the very region whose conditions future missions must understand more clearly. The mission therefore serves not only as a test of travel to the moon and back, but as a reminder that exploration improves knowledge most when it passes through the uncertain border between what is already modeled and what has only just become visible. The mission now grows quieter in the mind. The flashes on the moon recede into distance, not as solved events, but as points of light briefly seen against a dark surface that has recorded impacts long before any human witness arrives. Earth continues below, with its atmosphere, its oceans, its cloud cover, and its restless filtering of what enters from space. The moon continues beside it, airless and patient, preserving a cleaner trace of contact. Between them lies the cislunar region, not empty, not crowded in any familiar earthly sense, but filled with motion too small and too constant to notice without long attention. In that larger stillness, Artemis II becomes part of the same patient record. It carries human observers outward, lets them pass through shadow light radiation distance and return, and places them for a brief interval inside a wider physical reality that usually remains hidden behind sky and weather. The uncertainties do not vanish. They settle into their proper place. Some signals may prove temporary. Some may soften back into baseline. Some may remain and slowly reveal a deeper pattern only after many more months of careful comparison. For now, the near-Earth environment remains what it has always been, a field of small motions and occasional bright consequences, understandable only in pieces and only through repeated watching. The spacecraft turns home through heat and plasma, through measured risk and refined design, and the story itself comes to rest in that same measured state. not resolved, not alarmed, but attentive. The Sun remains active in its own rhythms. The debris continues on its unseen paths. Earth and Moon keep moving together through the same broad stream of material. And human understanding advances in the old way, through one observation, then another, until the background itself begins to speak more clearly than before.